be in the third quadrant, right? So both of them will be negative, which means if I count my fourths, I have pi over 4, 3 pi over 4, 5 pi over 4. Why is that option off the table? Why don't I even have to worry about it? Because when I talk about phi, it's running the z-axis, right? It only goes from 0 straight up down to pi, which is straight down. So the other options off the table, I don't actually have to worry about it. Well, that's where I want to run phi up to. Where am I going to start it at? I'm going to start it at 0.
Why? Like, we have a place, like, logically that seems right to start it at 0. Do we have something that specifically tells us that?
Oh, you're asking how do we know it's exactly at 0? That's a really, really good question. One of the reasons why we know that we want to run it from 0 is by looking at where the actual shape is. That is, we know that we want to start up at the top of the axis and run it all the way down to wherever we're stopping it at. So that's one of the hints we have. Another hint we can look at is exactly what we started with over here, and the other options that can make this true for us. The easiest way to think about it, though, is if we do visualize it and we think about where we want to start it at. I wouldn't want to start it down here, right, because I'm not going to catch my entire solid. Sorry, I stared at you for a second. Yeah, we got it. Okay. Let's go ahead. How is this one different than the ones we've done in the past? The row is not constant, right? What makes that true? Why do I have a row that's not constant? Because I've got weirdness going on, right, with how I'm shifting. I'm not centered at the origin. We're also going to see this kind of thing happen when we've got solids that are bounded by two different functions that also cause it. In this case, what's causing it, though, is this shift going on. Okay, so let's go ahead and set up the integral. I want to find the volume of this, right? All right, so all this junk. Okay, when I go to find the volume of a solid, it is the triple integral over some region E, and what goes on the inside? If I'm just looking for the volume, it's a triple integral, what goes on the inside? Is everyone okay with 1? I'm hoping so. 1 dV. So what the only thing I have to really do then is set it up. Which one goes on the inside? The rho. The theta. Which means all I have to do is plug in my bounds here. 0 to times phi, 0 to pi, 0 to pi. You feel like you can integrate this?
Don't we use that, like,
Do we feel like we can integrate it? Yeah, it looks suspiciously easy to integrate, right? Why? What are we missing? We're missing something that we have to put in, right? We have to add something in there. We'll multiply by something, I guess I should say. In the case of spherical coordinates, what do I have to put in with that 1? Rho squared sine theta. This is very interesting. So far, when we've gone over triple integrals, we've been neglecting to tell you guys exactly where that comes from, exactly why we need that. Now, before I go off on my little rant here, it's going to take us into the next section. Are there questions on how we set this up? Yes? Yeah, so all I was saying is that this is what we put in whenever we're doing spherical coordinates. What do we put in whenever we're doing cylindrical? R, right? And so these two things that we've been putting in, we haven't really talked about why. And the reason why is because what we're actually doing up here are transformations. This is going to become apparent, hopefully towards the end of class today, exactly why we have that, and exactly where it comes from. Huh? Oh yeah, yeah, whenever you do spherical coordinates, you have to put it in.
No matter what, if it's constant or not, like,
Yeah, again is because what we're actually doing when we translate over from rectangular to spherical coordinates is we're doing a transformation. We have done two transformations already. We have talked about transforming from rectangular coordinates into cylindrical and transforming from rectangular coordinates into spherical. So if what we look at today looks a little bit alarming, keep in mind you have already done it before. It wasn't that terrifying before. Okay, so when we talk about transformations, essentially what we're talking about is taking some point, UV, and I'll actually leave this off. We'll go ahead and look at it on the plane right here. In which we're not looking at an XY plane, but rather a UV plane. So this is the UV plane. All we're doing here is defining something other than XY. So we've got a UV plane. And what we're doing is we're transforming, that is, we are mapping the UV plane onto the XY plane. Then we're finding a link that takes one set of coordinates to another set of coordinates. This link you can think of as a function, and we write it as t for a transformation. The way this works is exactly like a function. So to show you a transformation in two variables, a transformation might be something like f of x equals x squared. I plug in an x value, and what do I get out? I get out a y value, and what's the number going to be? 4. So what I'm doing is I'm taking this point 2, and I'm mapping it by my function to the point 4. All I'm doing is taking one, I'm getting out another. I'm transforming it. Now, it works really well for one variable, so what we can do is talk about transformation for 2 as well. Now, in general, when we talk about one point, we can say we're transforming UV onto XY. However, we don't want to just talk about one point. More often than not, we want to talk about a whole set of numbers. That whole set of numbers, we're going to call the one over here S. And so we take this set of numbers S, and we transform them into a different set of numbers, R. The really cool thing about this is that they don't have to have the same shape. That is, what's really wiggly over here could be rectangular over there, or vice versa. So when we do a transformation, it doesn't have to have the same shape on either side. Just like over there, I plugged in 2, I got out 4, right? I get different things when I transform something over. Now, in general, a transformation T can be written as a set of functions. So that is, T can be expressed as some function, I'm going to write it as h of UV equals x, and g of UV equals y. So I think the best thing we can do is look at an example to show you that it's not actually that terrible. So for instance, for example, we can write that x is equal to u squared plus v, and y is equal to u minus 3v. And this is what we would call a transformation. What it's going to allow us to do is plug in different u and v values and find out what the x and y values that correspond to them would be. So to use it, we're going to look at the point, first of all, we'll look at 0, 1. Where 0, 1 is in x. That is, 0, 1 are coordinates in the UV plane. These are u and v. We want to find the corresponding x and y coordinates that go with this point. That is, if we transform this coordinate over into the xy plane, what would it look like? Well, what do you think I'm going to have to do to find it? I'm going to plug it in, right? So to use it, all I'm going to do is plug these points in. That is, I have x equals 0 squared plus 1. So x is 1. And y is equal to 0 minus 3, or negative 3. which means my corresponding point is 1, negative 3. Essentially what I just did is I said I started with the point 0, 1, and it mapped onto the point. No, I cannot. It would pain me to write that in the wrong quadrant. We're going to go ahead and move it here. 1, negative 3. So what I have done is I've taken a point in S, so bad, and I've come up with a point in R. Question. Now, does it look okay so far? Good. Okay, so what happens is T takes us from here across, and what we're really curious about are some of the properties that T has. Well, first of all, we say that if T maps every point in S to a unique point in R, that is, every point in R only has one point coming over to it. Do we know what that's called? If a function takes each thing in the domain to a unique thing in the range, it's called one-to-one. Now, let's talk about exactly what one-to-one is really quick. If each element in the domain is mapped to one unique element in the range. Now this is how it holds for functions. We were talking about transformation, we're going to use slightly different language, but to understand that, let's first of all talk about an actual function. The example we're going to look at for one-to-one is y equals x squared. Is each x value going to give me a unique y value? Let's think about it here. If I plug in x equals 2, I'm going to get 4 out. Is there a different x value I could plug in that would give me the same y value? What's the other x value that works? Negative 2, right? This function is not one-to-one because there are two values in my domain that go to the same value in my range. Now, when we talk about transformations, we don't want to be talking about domains and range, although technically we could. We need different language to talk about. We call the set we are mapping into the image of our original. R is the image of S. And so essentially what we can say here is if each element in S has a unique image in R that is one-to-one. Essentially, all this means is that when I map them over, each point in S is going to go to its own point in R. There's not going to be any reasons for it. If this is true, if this holds, then we say T is one-to-one. One-to-one is very, very, very important. I want you to think back. This is going to be a while ago. If a function is one-to-one, what does it have? It's got an inverse function. That is, if it's one-to-one, then if I go one direction, I can go the other direction as well. So if it's one-to-one, what I'm guaranteed is an inverse function. The inverse function is written as T inverse. So, if T is one-to-one,